Section 8.7, we will be reviewing how to find the limit of various functions and learning a new rule to help us find the limit when direct substitution or our other methods fail us. So what we're going to do is recognize limits that produce indeterminate forms, and then we're going to apply the new rule called L'Hopital's rule to evaluate the limit. So let's review a little bit. The forms 0 over 0 and infinity over infinity are called indeterminate because they do not guarantee that a limit exists. We cannot determine what the actual limit is if we get a form like 0 over 0 or infinity over infinity without doing extra work. When you encountered one of these indeterminate forms earlier in the text, you attempted to rewrite the expression using various algebraic techniques. For example, we tried direct substitution always first. So if we've got the limit as x approaches -1 of 2x squared minus 2 over x plus 1, if you plug -1 in and you square it, you get 1. 2 times 1 is 2. 2 minus 2 is 0. And then in the denominator, -1 plus 1 is 0. So that's how we get the indeterminate form 0 over 0. Our algebraic technique here was to factor and then cancel. So we're simplifying the quotient by factoring and canceling. So we factor that, and then we found a equivalent at all but one point function, which is 2 times the quantity x minus 1. Now if we take the limit of that as x approaches -1, put -1 in, you get -1 minus 1, which is -2, and 2 times -2 is -4. So that limit does exist, and it equals -4. What that means, if we were to look at the graph of this, which would be that, except at -1, it would have a hole in it, because x cannot equal -1. It makes a hole in the denominator, but we know it's a hole because we canceled it out. Remember, if something doesn't cancel, some denominator doesn't cancel, and the denominator could be 0 at that point, that's a vertical asymptote. But if we can cancel it, then it's a hole, and this function agrees with the original function at all but one point, so the function 2x minus 1, or 2 times the quantity x minus 1, is this purple line, and then if you add in the hole at -1, it's the original function. Either way, as x approaches -1, that y value is -4. It does have a limit because the y value from the left and the right both approach -4, even though at -1 there is no y value. The next example we have is 3x squared minus 1 over 2x squared plus 1. As x approaches infinity is what we're trying to find the limit. So infinity squared times 3 minus 1 is just a big old infinity, and then on the bottom we have another infinity. So try to factor and cancel, and that's not going to help. So what we want to do is notice that the degree of the top is equal to the degree of the bottom. So that should just equal the coefficients of the x squared. Remember the shortcuts: if the degree on the top is greater than the degree on the bottom, then there is no limit. And that's if we're trying to find the limit as x approaches infinity. Or if the degree on the bottom is bigger than the degree on the top, then the limit will be 0. But if they're equal, then the limit will just be the coefficients. Okay, so we know this is going to be 3/2 using our shortcut. But let's say we forgot our shortcuts, or the shortcuts don't work for this one. Another method is to divide everything by the highest, x to the highest power in the denominator. So divide each term, divide each term by x to the highest power in the denominator, which is x squared. And then simplify. And then find the limit as x approaches infinity. And the limit of 3 is going to be 3, and if you put infinity here, if you put infinity here, infinity squared is infinity, and then 1 over a very huge number, that will approach 0. And then here, the limit of 2 is going to be 2. And then putting infinity in here, again, we get 0. So it's 3 minus 0 over 2 minus 0, which is 3/2. So remember those techniques. You'll be using them. We're not going to be totally avoiding all of our old techniques. So this is a good review for the AP test and for your assignment. Be familiar with and continue to use those old techniques that we've been using. You can extend these algebraic techniques to find limits of transcendental functions. We were doing limits before we even learned about functions like e to the x. So let's make sure we know how to use our original techniques for finding the limit of some new functions. E to the 2x minus 1, that can be thought of as e to the x squared minus 1. So factoring will work for this one, because this is like x squared minus 1. So it's going to be a plus 1 and a minus 1. And we'll have e to the x and then e to the x, because e to the x times e to the x is e to the x squared, which is e to the 2x. And so then the denominator will cancel. And then we can find the limit. Remember not to use equal signs because I'm not continuing to write the word limit in between. So now plug in 0. E to the 0 is 1. Anything to the 0 is 1. Plus 1 is 2. I can use an equal sign here because I did rewrite the word limit, and the limit of e to the x plus 1 as x approaches 0 is 2. All right? Oh, I could have written that work down here. Sorry. All right, so, however, so we're at this dead end. Not all indeterminate forms can be evaluated by our algebraic techniques that we've used. This is often true when both algebraic and transcendental functions are involved. Like here, this is called a transcendental function because it's an exponential function divided by an algebraic function. We can't factor and cancel, but if we just do direct substitution, we get e to the 2 times 0, which is e to the 0, which is 1. 1 minus 1 is 0 over 0. So what if we rewrite it like this? E to the 2x over x, using that technique of dividing by the highest power of x in the denominator, or x to the highest power in the denominator. You get, again, infinity minus infinity. Remember that the limit as x approaches 0 of 1 over 0 is infinity. I don't know if you remembered that. So we get infinity minus infinity, which is another indeterminate form. That might be one we haven't talked about yet. But infinity minus infinity is not 0 because the infinities might be different quantities. So it's indeterminate. So what are we going to do? We have a new rule to learn. It's called L'Hopital's rule. Mathematician L'Hopital, he was French. He discovered this idea that if you want to find the limit, you can use the idea that the derivative of the top over the derivative of the bottom, and we find the limit of that, it will be the same as the limit of the original function. So essentially, you're finding the limit of just the quotient of the derivative of the top and the derivative of the bottom. But you can only use it if you get an indeterminate form from direct substitution. So you always must use direct substitution first. And if you get an indeterminate form, then you can use L'Hopital's rule. L'Hopital's rule will not work unless the original function produces an indeterminate form by direct substitution. And this also is not the derivative of the whole function. We're not doing the derivative of the quotient like this, where we do low d high minus high d low. It's actually what you wish the quotient rule for derivative was. It's just the derivative of the top and then the derivative of the bottom, and then you take the quotient of them and then you do the limit there. So it's not a quotient rule. It's not really finding the derivative of the whole function. It's just a method to find the limit, a shortcut for finding the limit. So that's the theorem, the formal written out theorem. F and G are functions that are differentiable. We obviously would have to be able to find the derivative in some area around C that we're trying to find the derivative of. except maybe at c. That's okay if there's a hole at c or something. And the denominator would never equal 0, so we also have to assume that the derivative of the denominator would not be 0. So what they're saying is that the limit as x approaches c of the original functions divided by each other will equal the limit as x approaches c of the derivative of the f divided by derivative of g, as long as this is not 0, and as long as these two original functions are differentiable, at least at or around c. Also, it only applies if you get an indeterminate form. And here are some examples of indeterminate forms, like infinity over infinity, or negative infinity over infinity, and the opposite, infinity over negative infinity, or two negatives, or infinity minus infinity, or 0 over 0, or a whole bunch of other possible indeterminate forms like 0 to the 0, or infinity to the infinity. So there's a lot of indeterminate forms. Here's some more examples. 0 or infinity plus infinity is infinity. So these are not indeterminate. Infinity plus infinity is infinity. If you add up more infinities, you're just going to get a big infinity. If you subtract two infinities that are the same, then you get negative infinity. And 0 to the infinity is 0. And 0 to the negative infinity, because it's 1 over 0 to the infinity, which would be 1 over 0, approaches infinity. So those are all determinate forms. And these are indeterminate forms. Here's another one I didn't mention, 0 times infinity, and 1 to the infinity. Okay, did I mention, nope, I didn't mention this either, infinity to the 0. That's the only thing that's raised to the 0 power that doesn't equal 1. So be familiar with the determinate forms and also the indeterminate forms. Okay? As a final comment, remember that L'Hopital's rule can be applied only to quotients leading to either 0 over 0 and infinity over infinity. For instance, the following application of L'Hopital's rule is incorrect. All right, let's see. If you put 0 in, we get e to the 0, which is 1 over 0. That gives you 1 over 0. Is that an indeterminate form? No, it's not. What is that limit? That limit is infinity. If you use direct substitution, you get something divided by 0, that limit is infinity. But let's say we thought we could use L'Hopital's rule. The derivative of e to the x is e to the x, and the derivative of x is 1. And so if we try direct substitution now, e to the 0 is 1, and we get 1 over 1. We think that limit is 1. But we already know that the limit should be infinity. So that is incorrect. You can't use L'Hopital's rule unless you get infinity over infinity or 0 over 0. Let's do an example now. So this one was the one from before, e to the 2x minus 1 over 0. If we do direct substitution, we get 1 minus 1 over 0, which is 0 over 0. That's indeterminate. So now we can use L'Hopital's rule. So let's take the derivative of the top. So the numerator is e to the 2x minus 1. And the derivative, this is a chain rule, so it's e to the 2x and then times the derivative of the exponent, which is 2. And the derivative of 1 is 0. G of x is x, and the derivative of that is 1. So now we're going to rewrite this. Oh, the other thing is, don't ever use equal signs here. This is not true. This doesn't equal. Well, actually, this is equal if you write the word limit in between, because the limits are equal. If you write the word limit, then you can use this equal sign. But if you don't write the word limit, e to the 2x minus 1 over x is not equal to 2e to the 2x over 1. So they're not equal. You can use an arrow to show that you just, did some process or working in between, but they're not equal. All right. So these two are equal. And then let's do the direct substitution. Put 0 in. 2 times 0 is 0. E to the 0 is 1. 2 times 1 is 2. 2 over 1 is 2. So your limit's 2. Okay? That's L'Hopital's rule in action. Let's try this one. Ln x is another transcendental function. If we do direct substitution, we get natural log of 1 over 1 squared minus 1. Natural log of 1 is 0. 1 minus 1 is 0. Indeterminate, so we can use L'Hopital's rule. So the derivative of natural log of x is 1 over x, and the derivative of x squared minus 1 is 2x. Simplifying that, we multiply by the reciprocal of the denominator, so we get 1 over 2x squared. So now let's take the limit of that as x approaches 1. 1 over 2 times, 1 over 2 times x squared. Direct substitution gives us 1 over 2 times 1 squared, which is 1 over 2. And there's our limit. Before L'Hopital's rule, we would not have been able to solve any of these. Let's try this one. If we do direct substitution, negative infinity squared would give us infinity, and e to the negative infinity would give us, oops, I didn't write infinity in there, would give us positive infinity. E to the infinity would be infinity, so we get infinity over infinity. So we can use L'Hopital's rule. The derivative of x squared is 2x, and the derivative of e to the negative x is e to the negative x, using the chain rule, times the derivative of the exponent, which is negative 1. Now let's plug in infinity here. Direct substitution gives us 2 times negative infinity over negative e to the negative infinity. So that's going to give us negative infinity over negative e to the positive infinity, and negative divided by negative is positive, and infinity over, and then e to the infinity is infinity, still indeterminate. What do you do then? Well, the amazing, awesome thing about L'Hopital's rule is you can use it over and over again. As long as direct substitution keeps giving you an indeterminate form, keep using L'Hopital's rule. So apply L'Hopital's rule to this, which was the derivative of this. So take the derivative of this, we get 2, and then the derivative of e to the negative x times the negative is e to the negative x. The negative and the negative cancel out. So now direct substitution gives us 2 over e to the negative infinity, which is 2 over e to the infinity, which is 2 over infinity, and 2 over a really big number is just going to approach 0. So if you remember why they're called indeterminate forms is because sometimes as you do more work, infinity over infinity will give you different answers, and 0 over 0 will give you different answers. So there's no way to determine what that answer or result will be if you have an indeterminate form until you do more work. Here's your homework, page 576, 1 to 31 odd. And then the next day, we're not going to have another video, but we will have another assignment on this, so I'll give it to you now. We're going to do page 576, 33 to 61 odd, and that'll be due Thursday. Okay, that's all.